with some operations that usually go after the thresholding. So let's just run this code. It's from the previous class. I forgot to import everything. CV2. Might need this, and the usual stuff. So we have the image from the previous class, and this is the Sudoku image. It's a nice example of what we are about to do. Instead of using threshold binary here, I'm going to use the inverted threshold binary so that I get whites for the numbers and for the lines. And this image, as we can see, it is nice, but it could use probably some post-processing. So firstly, we are going to define some morphological operations. Morphological operations are usually done on binary images. This is a binary image where the pixels have a binary set of values, so they can be either logical 1 or logical 0. In our case, it is 255 or 0, or in the case of OpenCV. So what we can do is perform some morphological operations here that can help us with making the image a bit cleaner. The basic morphological operation we're going to use will be, we have the images in IM2. Let's rename this IM, and we have the result in result. So the result, we're going to do a bit of erosion on the result. The morphological operation erosion creates a kernel, a filter that checks the surrounding area of the pixels, and based on a condition it will either remove that pixel, set it to 0, or leave it. So it will basically reduce the size of the white areas. So to define it, it will be erosion result is CV2 erode, and we have the source image. It was the result image, and I think here it was an element. I will check if there is a default value. It's missing a kernel, so to kernel I'm going to the null for images, or I can just go with I need the default matrix, so I'll go with size 33 and try it like this. It worked, so now just to show the result, let's see what we get. Here it is. So I did maybe a bit big erosion here by a 3x3 kernel, but what is done is that in the image all of the pixels are reduced by 1. so it erodes in a way the white areas in the image. We're going to return to this later, a bit later, when we are going to build filters and kernels for convolution in the image, custom kernels. But for now, let's go with this default kernel. I think that I should be using some sort of a matrix here. Try it like this, 1 times 255, and now the result will be is the same, so it considered it a logical value. The other operation is dilation or the dilatation. It's the result will be with this function, so I will get we'll use the same kernel. It's practically 3x3 kernel, means that I'm using only the surrounding pixels around the image, and let's show the result. Here it is. It made all of the lines thicker. As you can see here, there was some noise in the image. These are considered noises where there are pixels that have some extreme values that need to be removed. So with with the erosion followed by dilation, we can actually remove them. So if I get the result of the erosion and dilate it, I'm going to get a bit cleaner image. Now it destroys the numbers, but for larger images it could give better results. So these are the two basic elements for morphological operations. These are the erosion and dilatation, and this will be the most used ones if you are performing image processing. There are others that are defined by OpenCV. So these operations are opening, closing, morphological gradient, top hat and black hat. There are some combination of erosion and dilatation. So opening would be dilate from erode from image. Closing would be erode from dilate from image. Then we have morphological gradient will be dilate of image minus erode of image. This will give the gradient the edges where the difference of erosion and closure. Then we have top hat. It will give the result is image minus opening of image, which opening is defined like this, so I can just copy this here to get it with the regular. And black hat is the closing minus the image. So these are how these operations are defined, and how we can use them is by using the function morphology x, which gets the source image. We can use this image here. It was the result. A bit unintuitively, but it is what it is. Then we have the output image. I think should be here, and we need to also define the operation. The operation would be for opening, it's morph open. For closing is morph close. Again, these are flex, they are numbers. Morph gradient, morph top hat, and black hat. So we have all of these here. Morphology X, the result, the operation would be any of this. Let's go with more open. And what else do we need? We need the same kernel as above. I'm going to use the same kernel and visualize the result. Here's the output. Aha, I forgot to. Here is the result. It's the same result as the thing what we did above. We can try the others. Just for the illustration, I'm going to copy them all here so we can have morph close, morph gradient, the difference, top hat and black hat. Here are all of the operations. This is the gradient, top hat, black hat. I think that it could be better if I use maybe a different image here. Let's try with apple. Here it is. This one. We can see more on the apple about what everything does, and probably I would use regular threshold on the apple. So instead of this, let's get the image. So the result had the one thing, the threshold, then we have 255 and CV2 thresh. Let's go with odds. I can't decide immediately on value, let it decide for me. So here it is, here is the threshold that I would invert the image first. So let's go like this so that I get, here it is, I get an inversion of the apple, and here is maybe more visually can be seen how these operations work. So we have opening, closing, not so much of a distance. In opening it tries to increase the black areas, in closing it will try to decrease the black areas. This is the difference, and top hat and back hat didn't give much. This is the difference between opening and closing. So these are the basic morphological operations that can be performed in OpenCV. They are quite nice for post-processing of masks. What I usually do when I need to make sure that the mask covers the full region of the object of interest is to just dilate the mask. But first I do a step of erosion, so this opening erode then dilate is something typical that I would usually do when I need to mask the object of interest on top of it so that I am certain that it's fully covered. Let me try doing something. So I have the apple here, I loaded it with 0. Let's load the apple again. I'll load it with 1, visualize it in full color without CMap, but first RGB to BGR. So here we have the apple. Now I have this image. I would add on top this one. Is the, let's name it open, and visualize open. And I would go with sad weighted ima 2,0.9 and open 1. It might give me an error, but let me try it. Visualize res, add weighted missing argument gamma, position 5, 1. The arrays are not the same, so what I will need is to create an image with the 3 channels so that I add a bit value, or maybe even get one of the channels of this image to be 255 to be equal to the mask. Let's do it like that. Let's go with the first one, equal to open. Let's go like this and then visualize this image. Okay, here it is. So practically what I did is 0 was red channel now. Make it everything that was covered by the mask 255 red, and the rest of it will have the red value 0. And here, as we can see, we are not covering the full apple, but we are covering most of it. So if I do opening and another dilation on the open, so like this, I will cover more larger area. Visualize this. The idea is that with dilation of the mask you increase this area, so you will dilate it as much as you need it so that it covers the full region. Okay, that's erosion dilation and the other morphological operations that are of some importance. Now, another operation would be the filtering of the images or the convolution between different matrices. This operation is somewhat basic. What we practically do is trying to smooth the image. So let me just illustrate one of these commands. I'm going to use the apple again and just use the blur command, which is uses a basic box filter, and what we specify is the input image and a tuple that gives the dimensions of the filter. I would go with, I don't know, 7 by 7. Here it is. Let me first, I'm going to place this in another image and I'm going to show both of them just so that we can compare. Okay, here is the first one, here is the second one. I think on the screen it will be obvious that the second one is a bit blurred. I think that increasing this would make it even blurrier, yes. So what it practically does, the blur, is that it goes with a matrix on top of this, with another image on top of this image, and performs some calculation. This matrix that is used is usually referred to as a kernel of the filter, and that matrix is actually the filter. How the calculation is performed is that we take a pixel, we take the surrounding pixels, and we multiply the values of each of the pixels with the values of the kernel, and then we summarize those, multiply them by a factor, and we obtain the value of the pixel. This blur is the simplest of all. It uses 15 by 15, or let me do it with 3 by 3. It won't be much, but it's a good for illustration, slightly blurring the image. It will use a matrix. Sorry, so it's something like this. This will be the matrix, so each pixel will be multiplied by this times 9, 1/9th of this value, which would create the average of this. So practically the box filter has ones here. And imagine placing this on top of the image here, calculating the 3 by 3 matrix with this, and the middle pixel will receive the value 1/9th of the sum of all of the pixels. So practically the box filter, normalized box filter, will give us the average of the surrounding pixels. Another pixel filter, would be the Gaussian filter, which can be called with another function. I'm going to comment this out. Instead of blur, we are using Gaussian blur, and we're going to get, it requires additional arguments, so I'm going to go with some default value here. Here is the Gaussian blur. It's similar, but instead of using this matrix 1 by 1, it uses a Gaussian matrix which visualizes in a way a Gaussian distribution. So Gaussian distribution, I think you've seen it. It looks like a sombrero, like a hat without the lower part. So basically it makes a normal distribution on top of this matrix in 2D and calculates the blur based on that. Then there is median blur, which surrounding, so here 11. Here it is something similar. The median blur will calculate the median of the neighboring pixels and we'll set that value in the pixel. And there is another filter worth mentioning, and that is the bilateral filter. Comment this out. So we have Gaussian median and it goes with the size, let's say with 11, then go with this 25. These are some values of the bilateral filter that give information on, so we have the diameter of the pixel neighborhood, what standard deviation we use, and the standard deviation in pixels. So this is for colors, this is for pixel, and when we run it we get a bit smoother image that tries to, so to say, even out the noises in the image. So these are the mostly used filters that we can actually use. So we have Gaussian blur, median blur, and the bilateral filter. Let me try with some different. Let's go with 5 and 10. We will get different results. Not so much. Let's go with larger area. It smoothens up the image. Now, what you must know is that by smoothing the images, you're actually losing some information from the images because you are getting some aggregation and losing some information about the pixels. Although by nature, when you are taking an image with a camera, it's usually noisy. There are some noises because of the fluctuations in the sensors that are receiving the light from outside, especially for digital cameras. So when you perform some image processing operations on the images, especially for machine vision application, you must first do some filtering, do some smoothing of the images in order to reduce these noises. There will be extreme values in some areas, like maximal or minimal values, black and white noise pixels, which need to be evened out. So this is practically done with these types of filtering. Nice thing is that we can actually define our own filters. So this is called linear filtering because there is a linear operation between the images. So what we would do is define a filter. In the next image, let me just copy this. We have functions for this, so we will need to create a matrix it will be like kernel from, let's say, size 11 by 11, and we specify the destination type float32, and this is our filter, which is with ones, and we can, to make it a box filter, now we only need to divide it by the value, so it will be divided by the number of pixels, and now we will have a box filter of size 11. If we want to define the size, let's go with, and just change the values. This is maybe the more appropriate thing to do here, and what we do is have a result equals to filter 2D. We have the image as the source. I'm going to need another parameter, the destination depth. This would be -1. We're going to use the same depth as in the previous image, and then we're going to need the kernel for the filter and visualize the result. No, my mistake, I copied the wrong piece of code. This is what I need. So what I need is to visualize the image and visualize the result. Here is the blurred image with the box filter. Now I'm going to get this image in this color space. Oh, let's copy the code. I'm going to get it in 0 color space, delete this, and have the box filter on the grayscale image. I'm going to need CMap. Here it is, the blurred image, and what I'm going to do next is define my own kernel. So this kernel I will comment out and make something like this, -1, 0, 1, -2, 0, 2, -1, 0, 1. This. I'm missing something. Filtering with care. Typo. Can I do this? So try by let's go like this. I'm going to set it manually. This one, just once, and then like this and try it out. And this is nice. I destroyed the image. Let me first invert it. I'm reading the image and okay, now I got something. With the filter, salt. Okay, so I'm having this image 255 and I'm using this kernel. Here's my mistake. It's supposed to give me the edges of this image where there is a sharp value, or I can just go with kernels. Our kernel size should be 3. This is probably my mistake. I'm getting there. So I have kernel size 3. I have this float image. Maybe I would get date image. Getting there. Now this -1. And what I need else is maybe go with this one, increase these values. No, it didn't work. For some reason I'm making a mistake that I can't really identify. So let me print out the kernel. Yes, needs to be float. Oh, there's my mistake. Zeros. Here's the matrix and here is what I wanted to achieve. Okay, now again, if I do the same thing with switching, transposing the matrix and add these values together, I'm going to get an edge detection. This is practically the first derivative of the changes of the pixel values when you're going row by row. So as I'm going row by row, if it increases in value, I have a large white value. If it decreases in value, I'll have a lower value. So when the filter creates the result, I don't know if it's supported. It's not probably, or it goes below 0 and neglects them. Print out the result too. So it's mostly zeros. Print result. (300 by 300) it's 7, so it goes down. It still keeps the image to be unsigned integers, so everything that's below 0 goes down. What I try to do here is first derivative in the horizontal line will give you the edges of the image. The first derivative is the changes between the pixels. So what it will do is take -1 times that pixel plus 0 times that pixel plus 1 times that pixel and do this in a 3 by 3 manner. This filter is actually the X component of the Sobel filter, which is a filter that is used for edge detection. If we don't want to manually define it, we can actually use the Sobel function, which is Sobel of the image. It needs a grayscale image, so it's our image, destination depth -1, 0, 1, and I think this would do it. Kernel size 3. Let me check if it runs. It runs perfectly. And then the result of Sobel. Let's show it. I don't need these prints anymore. Here is the result of Sobel, of one component of Sobel, and another component of Sobel will be 1, 0, result 3, and this will actually do the convolution with the matrices that I mentioned above. So this will be result 3. Here it is, and if I summarize, here it is, the full edges that were detected using the Sobel method. There are different types of matrices that can be defined. Practically, in order to calculate the first derivatives, what you need is something like this: -1, 1 for the x-axis and -1, 1 for the y-axis, or you can add 0 in between. It will calculate you the first derivative of all of the pixels in line. Okay, and the best function for using that you can use actually in for edge detection is actually the Canny edge detector, which is a standard. It has good performance. It uses some filtering and then uses some post-processing. So to create this image using Canny, we're going to use, load the image again and make it here, make it white, and we're going to go with the Canny edge detector. We have the first image, the result will go here of Canny, and then we are setting two thresholds, low threshold and high threshold. The one is to detection over which result for the first derivative we will have value of 1, and the other is how to connect the images. So this will be, let's say, 60, 50. You can experiment with this value. Let's go with kernel size of 11 and visualize this result. I don't need just the result here. It should give a nice edge detection, so I maybe 20 here, smaller, 100 larger, 60 would go here. You'll get lower, 5 to get more lines. Probably the JPEG image is broken, but what is nice here is that the edges are actually 1 pixel edges, and they can actually be identified as lines. Now, as you can see here, it gets nice line of the apple, but it also gets some lines in the inside, and that is based on these threshold values here. And what you can do is actually perform some blur of the image like this in order to smoothen the image. So I'm going to perform blur on the image here and get a maybe more smoothed out result for the lines. This is why you need the blur, actually, to remove the noise from the image and make the other algorithms more successful.